All right, welcome back to our section on hypothesis testing for two means. In this video, we're going to take a look at performing hypothesis tests on the means for two independent samples. So in our last video, we looked at dependent samples, a matched paired or pairs or a paired t-test. For dependent samples, for this one, we're going to look at independent samples. Oops, got to. All right, so for this part, our samples are going to be independent of one another. So we're not going to have that before and after or some pairing of the data like we did in the last video. So, and with this one, because they are independent of each other, our samples don't even have to be the same sizes. So we are allowed to have two different sample sizes for each of the groups that we're testing, doing the hypothesis testing on. Whereas with dependent, they had to because they were paired up. So there was a natural order to them having the same sample size. When they're independent, they don't have to have the same sample size. They can, but it's not going to be an inherent requirement. So in this part for independent samples, there is the idea that's known as pooling. So since our independent samples don't have to even have the same sample size, we're going to have to know about the assumptions we can make about their variances. In other words, the spread of the data for the population, the squared spread of the population data for each data set. And if we operate under the assumption that the two populations have equal variances, in other words, the variance of the, or actually it should be squared, sigma squared x and sigma squared y, I apologize for that, then we use what's known as pooled or weighted estimate of the common variance. Think of this like pooling, like if a group of friends pool all their money together to buy something that they can all enjoy, like, let's say a pool table. How's that? So they all chip in to buy this pool table, so they pool all their money together in order to buy something that they can all use that is more expensive than too expensive for one single person. However, the issue with pooling your assuming that they come from equal population variances is that the p-values that you obtain through pooled tests can be significantly off if the population variances are in fact not equal. So in other words, if we say, yeah, we're going to use a pooled independent samples and they weren't, the population variances were not in fact equal, then the p-values that we get are going to be significantly off, which could have severe negative consequences to our hypothesis testing. So as such, unless otherwise stated, the examples in this section, we're going to assume that the population variances are not equal. So there are tests that you can perform called F-tests. Maybe have a video on them, a supplemental video in the future, but for right now, we're going to assume that the population variances are not equal to each other. So in other words, we will not be pulling our data together. So some assumptions that we need to make for independent samples is that the two samples are randomly chosen and independent of each other. So again, we cannot have any sort of natural pairing of the data. We can't have a before and after for independent samples. Our population distributions are approximately normal, or our sample sizes are large enough. In other words, each of these samples that we obtain are 30 or higher. So very similar to some of the other ones we've talked about in the past, where once we get that magic number of 30, our assumptions will work out. Our test statistic is the difference, the mean of the differences divided by the square root of our sample variance of the first data set over the length of the data set, plus this variance of the sample variance of the second data set divided by the number within that sample, that data set. This is our standard error, the square root of this lovely looking fraction down here. So our degrees of freedom that we get from for our test statistic, which helps calculate our test statistic and p-value and all that, is this lovely complicated formula where the V1 and V2 that you see are those fractions that were in the denominator for our test statistic on the last slide. In terms of the values that we get, in all likelihood, we're going to get a value for the degrees of freedom that's a decimal. And if you are doing this by hand, which my hat's off to you, I don't want to do this by hand. You would round the degrees of freedom down to the nearest integer. However, with technology does not have to necessarily worry about that too much. So your statistical software might be able to handle it without rounding it. If working with pooled variances here, which again for our purposes we're not going to do, our test statistic is found by this lovely looking formula here. This is the pooled variance, S sub p squared is the pooled variance, which is the degrees of freedom of the first sample times the variance of the first sample, plus the degrees of freedom of the second sample times the variance of the second sample, divided by, this is the combined degrees of freedom for both samples. So again, we're pooling our variances, we're pooling all of our resources into one big pile, so to speak. We just combine our degrees of freedom. We will not be, for this section, unless otherwise mentioned, we are not going to be working with this information here. Plus, it'll all be on a program anyway, so. All right, example 2, a local store claims that the waiting time for its customers to be served is the lowest in the area. Competitor store checks the waiting times of both. Sample statistics are listed below. At the 5% significance level, test the local store's hypothesis. We are going to assume that the population of wait time for both places, the local store and the competitor, we're going to assume that those populations are normally distributed. And we have random samples here as well. So, all right, so local store claims its waiting times to be served as the lowest in the area. Competitor store checks the waiting times of both. So our null hypothesis is that the wait times are equal to each other. And for our alternative hypothesis, the local store says its time is less than the competitor. So for our alternative hypothesis, that means that the mean of the local, which we'll call X, is less than the mean of the competitor, which we'll call Y. So in other words, for our null hypothesis, the differences is 0. For our alternative hypothesis, if we subtract the mean of Y from both sides, we get the difference is less than 0. So this is a left-tailed test. We have the mean of the first less than the mean of the second. So the mean of the local company less than the mean of the competitor. So we're going to input this information. These are independent samples, keep in mind. So our significance level, I think, was 5%. Yeah, 0.05. Our difference in population means was 0. The samples here are independent, so we'll select option 2. And we did say that the mean of the first is less than the mean of the second, so it's a left-tailed test, so option 1. And for this one, we are entering summary statistics. We have that table there, so option 2. We'll look at data sets in the next example. All right, the population variance is assumed equal. This is the part where we can have the option to pool or not. And again, for this section, unless it says otherwise, we're going to assume the answer is no. So here you do have the option, though, for 1. If you select 1, that is using a pooled variance. But we're going to use option 2. So the mean of sample 1 was 4.7. The standard deviation is 0.8, and there were 15 in that first sample. For sample 2, we have 5.2 as the mean. We have 0.7 as a standard deviation, and the sample size is 12. So again, notice the sizes don't even have to be the same with independent. All right, so we have our mean of sample 1, our sample standard deviation, just reprinted that. Here's our information we're going to look at for our decision making here. So we have a test statistic of negative 1.7303. Our critical value, negative 1.7088. So our test statistic is in that rejection region. Came pretty close, but it is in that rejection region. Our p-value, 0.0480, 4.8%, less than the 5% significance level. And our 95% upper bound, the largest difference we would see is 0.0062, which is not include the value 0. So if we created a 90% confidence interval, the two-tailed typical confidence interval, for 90%, the one on the right, the second value, would be this negative 0.0062, which means, again, our confidence interval would not contain a hypothesized mean difference of 0. So here's our information. And again, every single one of them has the same conclusion. We reject the null hypothesis. So our differences here are statistically significant. So at the 5% significance level, we have sufficient evidence to reject the claim that the mean wait times are equal and conclude our evidence supports the claim that the mean wait times at the local store are less than they are at the competitor. So they are statistically significant enough that it did not happen just based on dumb luck and chance alone. So we do have evidence that the mean wait times at the local store are less than that they are at the competitor. Example 3, yellowfin tuna were caught from 2 different areas and the weights of each are listed. Test the claim that the mean population weights are different at the 5% significance level. So we have some values in the first area for weights. We have some weights of the tuna in the second one. We're going to test the claim that the means are different. So, didn't want to do that. I must have forgotten to label. So our null hypothesis is that the means are equal. And if they're different, the alternative hypothesis is that they're not equal. So we're not saying greater or less. We're just saying not equal. So this is a two-tailed test, and we're going to enter in the data. So our significance level, again, 0.05, right? Make sure I get that right. Okay, good. Our difference in population means, again, we're saying is 0. These are independent samples. And this is a two-tailed test because we're just saying that the means are different. They're not necessarily less or greater. This time we have the data sets, so we're going to select option 1. And again, pooled variance, no, we're not going to assume that the population variances are equal unless it tells us otherwise, or we perform like an F test or something like that. So select 2. All right, so our first one is area 1. We have 30, 67, 49, 39, 80, 35, 53, and 41. And then we're done with that. So our next data set, we have 48, 52, 53, 54. We got that twice. 51, 55, 49, and undo. So hit the U, 49. So again, notice that I made that mistake. I hit the 1 and not the 4 and put a 19. So I undid it and made it now so it's 49. So please make sure you're careful. I did not do that on purpose. And another 49. Okay, now we're done. All right, so this one will give us the means and sample standard deviations for each. Here is the important stuff. We have our test statistic, negative 0.3983, our critical values. So notice our test statistic is in between the critical values. It's not inside the rejection region. Our p-value, pretty high. So our confidence interval, since it is two-tailed, this particular one does give us a confidence interval, or 95% confidence interval. Notice a difference of 0 is in between negative 16.7 and 11.8. So, again, every single one of these, this is not in the rejection region. This is way larger than 5%. And our confidence interval for a two-tailed test, it does contain the difference of 0. So we do not reject the null hypothesis. So at the 5% significance level, we do not have sufficient evidence to reject the hypothesis that the mean weights of the yellowfin tuna are different. Include that our evidence supports the claim that the mean weights are equal. Again, our evidence supports it. It doesn't prove it. It just, we have evidence to believe it, that the mean weights are in fact equal to one another. So, all right, that about does it for this video. Thank you for watching. I'll see you next time.